Alright, next up are derivatives of trigonometric functions. So mostly we're going to be looking at sine and cosine, but then we'll look at the other ones also. We're also going to be looking at some applications of that with simple harmonic motion and the derivative of acceleration. So if we want to find the derivative of y equals sine of x, we're going to do this algebraically first using our definition of derivative. Notice we're plugging in x plus h. Now to solve this, we're going to need to remember, just review this from pre-calculus, our sum formulas. So here we're looking at the sine of a plus b, which we'll be able to split like that. And so splitting that sine of x plus h up, we're going to have sine of x times cosine of h plus cosine of x, sine of h minus sine of h. So if we factor out that sine of x and do some simplification here, we're going to be able to split this up since this is a product here, where in our first one, notice that what they're doing is they're taking this plus and they're splitting it up. They're basically putting that h on both sides and making this into two different things, and then they're also factoring out that sine. And over here they're factoring out the cosine. When we do that, notice sine of h over h. This is the same limit that we looked at before. That limit is equal to 1. Cosine of h minus 1 over h is going to be equal to 0. And so we're left with sine of x plus the sine of x times 0 plus the cosine of x, which is just going to leave us with the cosine of x. So notice that the derivative of y equals sine of x is equal to cosine of x. Now we could do a similar proof for cosine, and we'll find that the cosine of x, its derivative, is negative sine of x. So basically they have the opposite function for their derivative. We can also look at the derivatives of other trig functions, which can be proved using the sine and cosine derivatives. Basically the derivative of tangent is secant squared x, and the cotangent is negative cosecant squared x. So notice that tangent goes to secant, cotangent goes to cosecant. The tangent is positive, cotangent is negative. Over here, kind of the same idea. Secant will give us secant tan, but if we're dealing with a cosecant, we'll have cosecant cotangent. Also, all the cos are going to a negative value. Cotangent, also if we look back at the sine, cosine goes to negative, positive, or sine goes to a positive cosine. So that's one way that we can remember these. You will need to memorize these fairly quickly. Also remember, we're always going to keep our calculators in radians unless specifically told to find an answer in degrees, because pretty much calculus is only going to work, these derivatives of sine of x and cosine of x only work when we're measuring in radians. Okay, so here's an example of the derivative using sine. Now we're quickly moving away from that simple problems there. In this one we're going to have to involve the use of the product rule. And so we take the derivative of the first, 2x, and multiply it by the second, and then add it to the first times the derivative of the second. The derivative of sine we saw was cosine of x. And that's it. For the second one, we have cosine of x over 1 minus sine of x, so we're going to employ the quotient rule. Notice here we're using u as our variable, not y, and so we're saying du dx instead to be true to our variables. Okay, we start with the derivative of the top. Derivative of cosine is negative sine times the bottom, minus, because of the quotient rule, keep the top and multiply by the derivative of the denominator. Since this is the derivative of sine of x, will be cosine, but be careful with this negative. Derivative of 1 is 0, but we're left with a negative cosine of x. And we put all of that over 1 minus the sine of x squared. Now we can simplify this, and notice that you're getting sine of x squared plus cosine of x squared, which is actually 1. And so this is simplifying. If we move that out in front, 1 minus sine of x over 1 minus sine of x squared. We can simplify further because of that exponent, and we're left with 1 over 1 minus the sine of x. One of the ways that we see trig functions used is in simple harmonic motion. So, like for example, we have a spring that's hanging a weight, and that weight is moving up and down. And so it's being acted on by a couple of forces. The spring is pulling it up, but gravity is pulling it down. Now in this problem, we're having this modeled by this equation here where s is position and t is time. And so we want to look at the velocity and acceleration in this problem and describe its motion. So first we're going to look at our derivatives here to find our velocity and acceleration. So the derivative of cosine is simply negative sine, and so 5 gets carried down. Same thing with the derivative of acceleration then, positive sign, so we keep the negative sign. Now notice here our derivatives for position and acceleration are opposites of each other. And when we had a polynomial function, we eventually cycled down to 0 in our derivatives. But with a trigonometric function, a lot of times we'll just keep cycling around and around and around and keep coming back to the same things. Now when we think about the motion here, we can think about a few things. First we can think about its position. As time's passing, it's being pulled down between a position of -5 and a position of 5. The amplitude then we can think about as being 5, and the period of the motion would be 2 pi. We can also think about what the velocity is doing to this. The velocity, it'll be the fastest here in the middle. Okay, here at 0, the rest position is when it's going to be the fastest, but it's going to slow down to 0 at the highest and lowest points. The acceleration is, since it's being pulled down by gravity and pulled up, then these forces are trying to act on each other. Now, when we're at 0, the rest position, the force of the spring and gravity are going to be balanced out. And so we're going to get an acceleration of 0 when we're at the rest position. When we're at the maximums and minimums, that's where we're going to get the highest acceleration, the greatest magnitude on those. If we also think about acceleration as going towards a certain force, when the spring is below here, the spring is what's actually pulling it up, and so the force that's acting on it, causing it to accelerate, is the spring. Whereas when we get to the top, acceleration is going to have the most force on it, and it's going to be pulling it down. And when we're in the middle, it's going to be balanced out. Another value that we'll look at is jerk. Jerk is the derivative of acceleration, so it's kind of like our fourth derivative of position. But we'll think about this as the derivative of acceleration. Jerk is what you feel when you have a sudden change in acceleration. So we don't normally feel acceleration if we're just sitting on the ground. We feel like acceleration due to gravity. There's nothing causing a change in acceleration. But when you're riding in a car and we change direction or we speed up or slow down, we feel a jerk. So if we think about the force of gravity being -32 feet per second, the jerk then would be 0 because the derivative of -32, a constant, will give us 0. But in this last problem where we just saw that spring moving up and down, the derivative of the acceleration there is going to give us 5 sine of t. And so we're going to see that jerk happening where the acceleration changes direction and sign. So notice the jerk is going to be always changing in this problem. Now we also have derivatives for other trig functions, but we're not really going to be using them very often.